And we've saved the best to last. Chris Engelbert from Germany, from München?
No, near Cologne.
From there?
That's probably the same area.
Ah, okay. I knew it was close.
Yeah, it's close enough.
It's close enough. So Chris works at Hazelcast, and a couple of interesting facts about Chris. First of all, Chris has been ill since Monday, so we have to be very kind to him. If you're sitting too close to the front, you might, if he starts coughing, you might need to sit a little bit back. Otherwise, you take something you don't want from GeekOut. Chris, when you're ill, there's always a lot to do when you're ill, right? Yeah. This is Chris's third conference in 3 days. So this week, Chris is being very much like Venkat. So without further ado, I'll hand over to Chris. So everyone, please stand up, show your appreciation to Chris.
All right. So what we're talking today is distributed computing. Distributed computing is where we're heading to because data are getting bigger. We can't store them anymore in just one computer. We're ending somewhere at the end of Moore's law. We're coming to this in a bit. Scaling up doesn't work anymore. So we need other ways, and distributed computing is one of the ways. So a few facts to me. Just call me Chris. It's a German name. Probably nobody can take it right. Even the GeekOut badge is totally wrong. Finally, I have a proof for that. I'm doing 8+ years of Java stuff, mostly performance, GC, traffic, TCP traffic and stuff. I'm coming actually from the gaming industry. Went through travel management. Finally, went up at Hazelcast somehow. So our space trip for today is we're looking a bit in Hazelcast as a framework itself. So a short overview: what is Hazelcast? Does someone actually work with Hazelcast? Ever tried it so far? One? Oh, that's not good. We could change that. So the second part is distributed computing. We have it will be some overview of distributed computing at all. Where we went to, where we're coming from, and the next 3 points, distributed executor service, entry processor, memory reduce, are more to the Hazelcast implementation. So we have different ways of doing distributed computing in Hazelcast, and eventually all of them will have some live coding, and eventually we're coming to the questions, I guess. So as I said, we're having a quick look at Hazelcast. So we're just picking the diamonds. Hazelcast itself is an in-memory data grid. So we have some competitors. I don't name some of them. What we do is normally we transparently partitioning data. Partitioning data means it's probably like sharding in relational databases. Sharding is something nobody wants to do in relational databases. We're doing totally transparent. To make it easy, we have implementations of all Java collection APIs. So it's Java util set, Java util map, and just transparently distributed on the cluster itself. And with the executor service and all that kind of stuff, we're a distributed computing platform. So why do you want to use Hazelcast? As I said, we're automatically partitioning or transparently partitioning your data. We are fully fault transparent. So if node fails down, or if a node fails and you would expect to lose data, we're always just activating some backups, and we're always available. As I said, we have synchronous backups. You can also have asynchronous backups for higher fault tolerance. So it's always a trade-off between fault tolerance and how many synchronous or asynchronous backups you want to have. We are fully distributed. The more nodes you have, the better it is. The more distributed heap you have. And we're using only in-memory because we are aiming for highest available speed or highest possible speed. So as I said, we're partitioning data. That means if you have different nodes, you always have an owner of a value, and you always have somewhere a replica, at least one. You can set null, set 0 backups, but nobody would recommend that. It's fully transparent, as I said, so you just put in some value. We're getting the consistent hash key, and we're just distributing in the cluster. So as I said earlier, scale up doesn't work out anymore, even if Oracle tries to say something other. But scale out works. So what we do is we're not trying to get the biggest server, but we get commoditative hardware and in a bigger, or how to say that. So you try to have more servers instead of one bigger one. That is the actual idea. That even makes sense because you can run the same operation on parts of data simultaneously, which means you have a speed up. So why in-memory computing? Yeah, this is a chart from 1980 to 2013. It shows once the typical size of memory, so size in megabyte. As you see, the violet line, it goes up and up. So we end up in 2013 for typically 16 gigabyte of RAM. But the price, the green line, just went down from $6,480 for 1 megabyte in 1980 to less than a cent in 2013. So we're heading to somewhere where RAM is so huge and so big that we should use it. Because, if the next slide shows it, we're having 2 HDDs, we're having HDD rate, and we're having RAM, 16,000 megahertz RAM, which is not even the fastest one. So you can even get faster RAM, but you see the speed up in compared to any kind of hard disk, so even SSD is way slower. So distributed computing is some kind of multi-cores on steroid. So if you want to build your own data center at home, it probably might look like this one. So you have a laptop, and you have some old servers maybe, and maybe you even have a PS3 and you don't like to play. You can just make all them together and say, okay, I want to distribute my work. When we were beginning, it looked like probably this. So we didn't have any kind of multi-CPU, multi-core operations. It was probably very easy to write your application. You just had a slow core. You probably had it for speed, but you never had the problem of any kind of concurrency. Then the first multi-core type of operation came in when we had the i386. At that point, it wasn't really multi-core, but the idea was the same. You had integer division or integer operations, and you had floating point operations, and they tried to divide it. And you had 2 cores, and they were working in cooperation. Eventually, someone came to the idea, hey, if we have multiple servers, if we have multiple CPUs, we can put them together on one board. It was first CPU cluster, if you want to. Then Sun invented a new supercomputer, probably not the fastest one today. Amazingly huge, a lot of CPUs, a lot of servers. It was one of the first real clusters. So what the idea was, we're having multiple servers and all of them working in conjunction together. And where we're now heading at is cloud computing, or where we actually are. So cloud computing means you don't even have to have your own servers, but you, for example, can just buy or rent them from Amazon, from Google, from whatever. So you probably don't even have to work on your own hardware. It has its own problems, probably like sharing data resources, but I'm pretty sure it is the way we're ending up. So that is the introductional part. Now we're coming to the more coding part. Like, the whole cluster is in your hands. So this executor service, I think everybody knows the executor service from Java, the interface. What we did is we built a distributed environment around it. So the distributed executor service is an interface implementation for the Java util concurrent executor service. So it just behaves like any other executor service you would have in Java, but we extended it so you have an iExecutor service interface, which has some special methods like I want to run on all members. I want to run on just a few members, so you have a member selector. You can say, I want to run on a member that actually has, or is the owner for key foo. Simon is a nice example. He doesn't look convinced, okay. So as you would expect for an executor service, you can put in some Java lang runnable, you can put in Java util concurrent callables, you get futures back from callables, so that means you can have even distributed, or your callable gets sent to another node and it just behaves like it was executed locally. The only thing that you need to look at is your runnable or your callable needs to be serializable in some way. It doesn't matter if it is Java serializable or if it is some Hazelcast way or maybe cryo. It just needs to be serializable because we need to transform it into byte stream and need to send it, probably send it to another node. As I said earlier, you can have the same task on all nodes. You can have the same task on just a few nodes. And probably the executor service shouldn't work on data. We have better ways to do this. Because if you have changes inside of your runnable or your callable, you always have to lock around the data. And there are ways to get implicit locks. So how to print a node name on all nodes? Who was in the talk from Venkat this morning for Java 8 lambdas? OK, you know what it is? I hope the rest understands lambdas somehow. So we create a runnable, and the only thing the runnable does is it prints the name of the member node. And we get, say, Hazelcast, please give me the executor service with the name default. It's just a random name. You can set even whatever. So you can even call it foo if you want to. It's just like we always have a configuration, and you set up the name on the configuration, and you can access the configuration via name. And then, as I said, you see I used executor service because on that way I said execute on all members. I could even cast it to executor service. It doesn't matter. It's just an extended interface. And I put in the runnable, and the runnable gets distributed to all members, executed, and you're done. So I think we're coming to the code demonstration. I prepared all this, but I think we have enough time to just write it. So I just made some adjustments to make it nice Java 8 compatible. So as I said, your runnable needs to be serializable. So I made me an adapter which is actually serializable to just have the Java 8 runnable, which is an interface which extends runnable and serializable. So I get direct serialization. And we're creating a new class. That's called executor service demo. I have a nice template for all the Hazelcast specific stuff we're not looking into today. So just as a quick overview, I'm having a static method. It creates two members. So I'm setting up the configuration. I'm setting members only to my local computer, because if someone here in the network might have Hazelcast running, they would find each other using multicast, and I don't want to have that. And eventually, I'm firing up a Hazelcast node. So in this case, I'm creating 3 Hazelcast nodes in the same JVM. OK, let's see. So we want to do the printing of the name, right? OK. So no, maybe not the name. It's, we can do that. It doesn't matter. So I get the executor service. I'm asking Hazelcast for give it to me. As I said, we can even make it foo. It doesn't matter. And I want a runnable. And the runnable is, I think I have the rub method. No, not here. Give me a second. We're copying it from the other one. So what the rub method does, it just takes the Java 8 runnable and rubs it into the adapter. So I can send it over the wire. It's just to make it nice. So what I do is I wrap it, and I say, I have a runnable which actually does system, let me size out. I made it somehow different in the example. So let's make it hello from here. So does it work? Incompatible parameter types. Ah, right. It takes the I made it correct. So I get the parameter as the Hazelcast instance of the node as a parameter because I let inject it. And that means I can say that, like, let's put this to the next line, even this one. I can say that, which is the Hazelcast instance of the node I'm running on. Give me the current cluster, and I want to have the local member. And well, we can just let it this way, and there we go. And I'm taking this runnable and just put it into, we would execute on all members, and I'm putting in the runnable, and I hope it works. So let's see, it's compiling. So Hazelcast is starting up. It builds a 3-node cluster. That takes a moment. So we're at 2 nodes. The third one is joining the cluster. There it is. And yeah, stop it. And we see we have hello from here, member port 5701, 5703, and 5702. So it just took the runnable, distributed it to all the members, and executed it locally. So this is probably the easiest way of distributing work in Hazelcast. As I said, it's not good to work directly on data. Let's switch back to the demonstration. The next one is the entry processor. Someone worked with coherence? No, that is actually good. I never said that. So entry processor is probably the same thing as in coherence. It means you're having a special operation, you're sending it to a node, or mostly to a key owner, and it atomically changes data. So you don't have to lock around it. It's an implicit lock you just get. It's like lock-free data operations. You use it normally if you because it prevents external locking. You don't need to lock your data structure. In most cases. There are cases you probably need to lock anyways, so we're partitioning data, so if you want to work on multiple partitions at all, you don't get atomicity. But on the same partition, you can achieve that without even locking. It guarantees atomicity, as I said, on partition level, and it's some kind of a cluster-wide thread-safe work or thread-safe way of working on data. So it looks like, yeah, you can read it, I guess. So if you want to increment a counter atomically, normally it is like in plain Java you would use an atomic integer. So we even have an atomic integer for this case, so it's not a problem. But if you want to achieve this using normal Hazelcast code, you can even use an executor service, an entry processor. So what it means is you have an entry processor or the increment method, and I'm getting the map entry I'm actually working on, and my current value is incremented to +1, and I'm setting the new value. These are 2 operations, so read and write could, in theory, be broken apart by just running another thread. But it doesn't work or the way the entry processor works, it is guaranteed that the operation finishes before anyone else will see the new value, will see the key again. So what we do is we're synchronizing internally, or we're serializing internally the operations on the same key. So let's see again a code example. Switch slide. Let's create another one. Okay. Entry processor demo. That's it. Where's my template? There it is. So once again, I'm creating a 3-node cluster. My old one shut down. That is pretty good. Let's close this for now. And we still want to increment the value. As we learned today on Venkat's talk, we can do this using static methods, which is pretty cool. I'd really like that. So you can say void increment, and we get the map entry. It's string int, string integer entry, and we say, okay, our new value is new value is entry get value +1. We set new value and I made a mistake because the entry processor always gives back a value, so we can even make it new value. So what we can do is, now I have to look. I also have the adapter classes for entry processor. I'm totally surprised. I really did work out well. So what I do is I have entry processor, which is string integer. And same as for the last time, I'm stealing the wrap method. So let's put it here. And what we do is call it processor. And we wrap the entry, and we get the new. No, we wanted to make it different. We wanted to use the method itself. So we can even make it, it's entry processor demo, : and increment. That's it. Okay. And now we're getting the map itself. In this case, normally, as I said, it's a Java util map. So IMAP, we can look at this, is just an extension of the concurrent map interface, which itself is an extension of Java util map. So you can even downcast that to map. It doesn't matter. But as the same as for anti-process, for executor service, we have some special methods. For example, executing an entry processor on some key. So we need to get the map. We're asking Hazelcast again for the map, and we're using default again. We need to set some key. We had Simon, and we're just putting in integer of 0. That doesn't mean he is a null. It's just for incrementing. Okay, no, not. He's probably 100. So now we have a key called Simon, and that means we can execute on key, which is Simon, and we have the processor. And if I run this, we hopefully see that everything is incremented in order. Everything else would be bad for our use case. It's starting up again, and eventually we should see. Oh. We just missed it. That's always the case. It's so fast. So, yeah, probably I should start the right one, right? Nobody told me. So let's try again. Hopefully this time it's the red one. It's entry processor demo. That looks good. So where's my output? Oh, it doesn't do anything. Why? Probably because let me shortly look at my other example. I missed something, I'm pretty sure of. Right. Okay, yeah. I missed the count because I wanted to make it to show that it is actually incrementing in order. So I created some threads. So let's just execute this one. Let's go quickly over it. That could be nice in Java 8 for each. So what I do is I'm creating a thread on each node that increments 4,000 times. So we want to see something. And actually, I missed this line, which shows that it does something. So let's execute this one. That's always good if you prepare talks. You can just miss something and nobody cares about it, because you can show that it works. So there it is. Awesome. I knew it worked. So as you can see, even if I'm having 3 nodes and 3 threads that incrementing it 1,000 times, it's totally atomically. It's in order. Nobody tries to increment the same value 2 times, and the same. So there's no problem like if you forget volatile in Java, for example. That's the wrong one. Oh my goodness. There it is. Okay. The last one is the black magic from Planet Google. Google invented MapReduce in 2003, I guess, or 2004. And it was created because they were facing a problem. They had to process a huge amount of data, and they had to process it in a reasonable time. So what they had a big database of websites and keywords of the websites and information about that, and they had to present it to the user on every search. And every search is different, even if you're looking for Jennifer Lawrence, maybe. And they had to present it in a reasonable time. So they didn't have time to just filter for weeks and like, OK, please come back next year, or in 10,000 years, maybe. So the use cases are still the same. It's probably log analysis. It's data querying. Aggregation is a kind of interesting case because we're heading for a special way of handling aggregations. I will show that later. We have distributed sorting, which is kind of nice in ways like Google ranking works, or the PageRank. And the probably easiest way is just extract data, transform it, and load it into memory. There are probably even more. So in a simple step way, it means you're reading data in Hadoop from files, from a distributed file system. In Hazelcast from memory, you map or maybe transform it, so it's probably the same as in Java 8. And eventually you reduce the result to whatever you want to have. So in a bigger range of steps, it means reading, transforming, probably combining the values before sending them over the network. Grouping or shuffling means probably the same as partitioning. Reducing and collating is something special for Hazelcast and InfiniSpan. It means you can have a final operation on your reduced result on the caller node. This is especially for distributed systems and in real-time MapReduce, it's kind of important sometimes. So the basic way of how MapReduce works is this nice chart. It looks way more heavier than it actually is. What it means is we have 3 input sentences. Saturn is a planet, Earth is a planet, Pluto is not a planet anymore, actually. Sadly, maybe. So what we do is we tokenize or we split the sentence into words, and we emit the word as a key, and 1 as a value. So it's the hello world of MapReduce. It's a word count. We're doing the same for the second and third sentence. And then we're grouping. That's why it's not partitioning. It's grouping. We're grouping the words from the different sentences together and sending them to the same reducer. And the reducer says, OK, I've seen planet 3 times. That is pretty cool. So eventually you get Saturn is happened 1 time, is happened 3 times, A and planet the same, and not anymore, both 1 time. So in pseudocode, it looks like this. We have a map operation, which gets a document as a value. It splits up the document for each word. It emits the word and 1 as a value. On the combining side, which is, so combining means creating some intermediate result. Normally, you would send the word and the 1 multiple times to the reducer, even if it happens on the same node, like Saturn is a Saturn, whatever. So that means I'm sending Saturn 1 2 times to the reducer, which doesn't make sense. It is just traffic. So what you can do is you pre-combine the result to Saturn 2 and send just 1 value to the reducer. So as I said, combining is some kind of creating intermediate results. And the reducer just gets those intermediate results and sums them up and gives you the sum. Like Saturn was seen 1 time, but A was seen 3 times. If someone likes mathematics, probably you will like this one. I copied it actually from Wikipedia, I guess. If someone sees an arrow, please raise a hand. I don't know. No hand. That is good. So this is from one of the first Google presentations itself. It shows how the source code for MapReduce operations or programs in Google source code itself evolved. And it's just 2 years. So somewhere around 2002, MapReduce was invented. And as you can see, they rapidly started to use it in even more and more operations. And probably if we look at 2013, we might not be at 900, but maybe 10,000. I don't know how many programs are running at Google, actually. On the slides later on, there's a link if someone wants to see the full slide deck. It's actually pretty interesting. So let's go back to the demonstration. We have 24 minutes. That is actually good, because this is the longest one. So let's see. I also created this up front, but we do it in a better way. We do it together. So let's see. I'm just deleting. Oh, I already deleted it. So what I did is I have some data files. I'll just read them into memory, and it's lorem ipsum. I think that everybody knows lorem ipsum. It's a pretty interesting text. Nobody understands, but probably someone will find out how it works. I still think it's a shiffer. I just haven't figured out how it works. So what we do is we're starting by creating a mapper. So as I said, our mapper tokenizer mapper. Now I need to use a different name because I already have that class. So tokenizer mapper 0. That is actually a good name. It implements a mapper. Mapper, and we're transforming from string to string integer. As we have seen in the example, we're emitting a string and a value 1. So we know we always need the value 1, so let's probably create it up front, just for a nice way of looking at it. We want to say, where is it? Integer value of, there it is. Probably we should use 1. Okay. Now we have a map function. Let's make it a bit more this way. The map function, as I said, gets a key and a value, and actually you get a context. The context is used for emitting, and for later it will be used for some more things like reporting progress and kind of stuff. So what we do is we get a string tokenizer. And we give it the value, because the value is our document. We say, as long as the tokenizer has more tokens, we want to do something funny. But actually, we're making a bit more. The tokenizer has a problem. It stops. It also counts points and commas and all that kind of stuff. So we're just getting the token from the tokenizer. And there is a nice clean word that is actually a perfect name. So we have the word. And to make it more fault tolerant for spelling problems, we're just using the lowercase of the word, because we're just interested how often the word actually exists. And then we say context, emit. We're using the word and the previous value 1. All right. That is our mapper. I think it's pretty easy. Anybody understands this? Any questions so far? That's perfect. Now we're coming to the second part. That is actually map and reduce. So we have a word count, reducer 0. But actually, since we're creating multiple reducers at runtime, we have a factory. So this implements reducer factory. And we know our input string, our input type is key type is string, and our input value type is integer. And we want to aggregate to integer, or to reduce to integer, because we want to have a sum. So as I said, it's a factory. So it can create reducers at runtime. The nice thing about reducers is they are just existing on the node that actually needs it. That means we can have a word count reducer. It doesn't need to be serializable for that. The factory needs to be serializable, but the reducer does not. So we have extend reducer. And again, we have we have integer type, input value type, and output value type. So let's put this down here. And we get 2 methods. So the first method is called for every value that needs to be reduced through that reducer. So it seems like we probably have to have some intermediate state. This actually is important for reducers, because reducers are executed on a thread pool. So it's probably possible that they jump between different threads. It's just for visibility, for nothing else. So you can say count. And every time we get a count, a new value, we add it to the actual count. And eventually, we say, OK, no, it's count. Actually, we say, OK, when reducing is finalized and we've worked on all partitions, we know we have a final result. So please give it to me, whatever it is. So now we can create our first map and reduce configuration, which actually is a job tracker. So job tracker is some kind of the big brother, the IBM of map and reduce jobs in Hazelcast. It is used for resource configuration. So you can configure the internal thread pool of a job tracker. You can configure how the internal streaming process works and all those kind of things. We're just getting the default values for now. Beside the job tracker, we actually need the map for sure. So it's a string map, sting, yeah. It's articles, very important articles, we know that. It's map name, I guess, right. And we need a key value source. The key value source is the adapter between different data structures in Hazelcast and a key value pair. So it transforms any kind of input data in some kind of, or in a collection of key value pairs. So we have the source, and we have, so for all the standard data structures Hazelcast provides, we have some wrapper methods. Like like from list, from map, from multi-map, from set. In this case, we won't need from map because we have articles map. And with that, we can say, OK, now I want to have a new job. I know we're starting at string string. So I'm asking the job tracker, please give me a new job for that key value source. I think so that is clear so far. And now is the interesting part. If anybody ever worked with Hadoop, he knows that configuring a Hadoop job is kind of pain in the ass. So what we did is we made it kind of nice, a more Java 8 way maybe. So we're creating a result of strings in map string integer because we get a count per word. And configuring the job just means, let's put it here. Configuring the job just means telling the job, I have a new mapper, which is tokenizer, wokenizer. That's even a nice name. Tokenizer mapper 0. There it is. And I have a reducer, which is new word count, reducer factory 0. There it is. And eventually, when I have configured it, I say, please submit it. Submit actually serializes the complete operation, the complete map reduced job, send it over to the other nodes, and they are working on it. And we get a future, so we can either say future get, and we're blocking, or we say future add then. Add then actually executes the operation in background and in a reactive way we learned today. Reactive programming is pretty cool. It calls back when the operation is done. So the API is fully reactive programming-like. What we do is we're just writing it to the system out stream. I built a nice thing which is actually the two-string prettifier. It does nothing more fancy than just making it more readable. And it still says there's a compiler, but I think it's IntelliJ. Yeah, it is. OK, if we execute this, we probably see a result after a second. Sorry? The factory is incorrect. Why? Oh, yeah, right. Good point. We should get a null pointer, right? Yeah, we did it. That actually guarantees you a T-shirt. Give me your address, I'll send you one. Sadly, I haven't either stickers nor T-shirts. It's probably not a good idea. So word count reducer. Right, that's good. I see the audience is listening. So let's try it again. Actually, when I started, or when I did the code for in preparation, I did the same problem. So it's quite common to forget the new operation afterwards. You're so happy that you wrote your reducer, you probably forget to instantiate it. And where is it? There we go. We see there's a lot of unreadable words, and they all happened a few times. So this is actually good, but we still have the problem, as I said before, we're now sending the values per word multiple times because we're not combining them up front. So what we do is we're adding another combiner. It's a word count combiner factory, even here. It implements combiner factory. That's component factory. Combiner factory. And we have string integer. So same here, 3 types, key type, and the input and output type. Now we're doing it correctly. We're just starting with that. Word count combiner. And we're creating the combiner. The combiner is pretty much the same as the reducer, with one small difference. combiner. Oh man, it's not my day. With one important difference. A combiner creates chunks of data. So internally, we're having some real-time operation. That does not mean we're totally stream the results, but we're chunking them. So we try to keep the system at all busy. So if we have the combiner, it's an integer. We see we have something special to work on. It does not say finalize combine, but finalize chunk. That means we also have, well, probably have to reset it at some point. So we also have combiner int, we have a count, and every time we have a count, we add it, we have a new value, we add it. And for every chunk, we set the count. And afterwards, the reset method is called, and we say, okay, just reset the count. We don't have any fancy internals, so that is probably the easiest way. This is kind of new, so I slightly changed the API from 3.2 to 3.3 in Hazelcast. So before you had to store the value in finalized chunk, reset it, and then give it back, which is kind of weird. And to just make the combiner working, you say, okay, I now have a cool combiner and I want to use it. Which combiner? What? String in. Have I missed something? What did I do? Ah, that's it. It's not my day. Yeah, too many factories. And if I run this, the output will totally be the same, but if we would measure the internal traffic, it would be dramatically lowered. So the normal chunk size, I think it's every 1,000 emitted elements, we're sending a chunk to the reducer instead of every element, just because of the combiner, which means the output will be the same. We again have all the values, but we have lower traffic. Okay, so far so good. We have 10 minutes. So I'm getting back to my pre-written ones. So it took a bit longer because I made so many errors. I'm just a bad presenter, I guess. So let's see. We have a basic example. What I also have, beside the fancy lorem ipsum texts, I have some salary data, which is randomly generated, so don't expect them to be correct. We have the table of all the states, where the abbreviation is mapped to the real state name. We have 500 US citizens. Hopefully nobody of them is actually a real citizen. And we have the crime state by grouped by state. This is actually from the US police. I have a nice story about that afterwards, because they are not able to make their own code correct. So the first thing is, let me see, we have a person mapper. The person mapper does nothing fancy. It just maps through all values and applies some filter. So what we do is we're looking for someone whose name is probably the same as we said before. In this case, it's not Simon, it's James. And when I run this, you probably know why I said, hopefully this is not a real US citizen. I just found that samples on the internet. Maybe I should lower it to 2 to make startups faster. Come on. And there we go. That is the reason why I hope it's not a real person. Yeah, maybe not the best American name. So let's see. I think we can have one more interesting example, and then we have some Q&A. That's state mapping. So I think state mapping is clear. So we're applying a grouping of people by states. We can just execute this. I think it's not that important to explain it. So the code is completely online, so if anybody wants to have a look afterwards, he can totally do that. Or at least I will upload it. So startup should be a bit faster. And there we go. There's a lot of persons. And where's the state grouping? There it is. There is one. I think it's not Panama, right? But Panama would be nice. Maybe the next US state. So, well, in this case, we're just grouping by everything. But the mapper can do something else. So the mapper is not only grouping. I also told him, if I set up a state, please just filter by that state. So if I run it again, we're just finding people from California, which actually is a pretty nice state. So if you ever have the chance to get to California, do it. They have just one temperature, so even Fahrenheit doesn't care. It's just warm. And there we go. Just people from California. Way too much still. And I think we do one last, let me see. So I said earlier, aggregations will be kind of different in Java, in Hazelcast 3.3. So what we do is we're adding an aggregation API. That means the aggregation API is built on top of MapReduce, but it handles a lot of common cases. So what we do is we want to summon all the want to sum up all the salaries. That means we have a salary mapper, we have a salary combiner factory, reducer factory, and we have a collator which gets the final result. So we map to different keys to parallelize the process of reducing. That means we have a final collator which takes all the reduced results and creates the final sum. It does just get a collection of entries and eventually sums all up. So if we run this, it's okay. It totally works. Oh. It totally works, but the problem is we would have to write the same sum stuff over and over and over again. So we came up with some nicer way so we have a nice salary income. I would like to have that for my own. What you can now do in Hazelcast 3.3 is you're just creating the same result using the Aggregator API. So the Aggregator API, I need to change that a bit to make it readable, just means you get your map, in this case salaries, and what you do is you have a supplier. A supplier is some kind of an adapter to get key value to get a value to another value, or to filtering on that value. So our filter is all, which pretty much means, yeah, I'm just taking all the values. I don't care for that. And what I give it is a property extractor. So it is called for every value, and I say, okay, please give me the annual salary of that guy. If we look into the property extractor, it's just an interface with one method, and it says extract. So it's just a transformation from one type to another. And actually, the aggregation we apply is integer sum. So we know we have an integer, and we want to sum it up. And that means we're just calling map aggregate. We give it the supplier, and we say, we want to have that integer sum. And if I call this, it is totally the same result, but with way less code to do. This works for average calculations, for sums, for finding minimum, maximum, for sorting, and kind of other things. That's pretty good. So there's the same result. I hope someone noted it and can guarantee that it is the same. So as you see, we're heading to the same way as Java 8. We're trying to reduce as much code as possible and make it convenient for you. And I have 2 minutes 50 left, which is probably pretty good for some questions. Do we have a microphone? Yeah. All right.
Okay. I have a question about Hazelcast. I was checking documentation, and it's very unclear how it recovers the cluster after network partitioning.
How the cluster recovers?
Yeah.
If a node fails?
No, no. If you have network partitioning, so you have split brain.
Yeah.
And
okay,
you're
so
allowed
it's a
to
general Hazelcast question.
Yes.
Okay, okay,
yes.
no problem. So you're asking for how it works if you want to remerge two clusters after a split brain problem.
Yes.
Okay, so what we do we have a merge strategy. You can implement it on your own, or you can set up some predefined, like, latest value wins.
How you determine latest value?
How to?
How do you determine latest value? You use vector clocks?
Using timestamps.
But they are not reliable.
Yeah, they're not. That's the reason why it's probably the best way to implement it on your own. I think the implementer is the person who knows best what to do.
So that's the hardest part.
Yeah, actually, it might be hard. It might be a pretty easy solution. So one customer was like, we're reading all the values from database, and we're just caching values from database. So if we have a split brain and we need to remerge it, we throw away both versions and just read it again from the database. So maybe the final solution is easier than it seems first.
So for example, you had the example about counter. How you will solve this problem? If both clusters will continue to increase the same counter, how you will merge it?
I see. The actual atomic integer implementation in Hazelcast pre-allocates ranges of values. I'm not 100% sure how it does, but it pre-allocates and increments in that area somehow. Probably it's open source. Just look it up. I'm not 100% sure how it works. I haven't implemented it.
That's a great answer. Google it, come on.
Sorry?
That's a great answer. Google it.
No, not Google it. Just look at GitHub. Oh, that's mine, GitHub. The other one is github.com/Hazelcast.
Okay, we have 10 seconds for a final question. 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay,
We're running out of time.
I would go over slightly, but if we had a coffee break or something like that. But unfortunately, we don't. We have the closing. So I'd just like to say thank you very much for another awesome demo-driven session. And for those of you who don't normally give sessions, these are the hardest ones to do. And this guy's not feeling very well. So let's give it up for Chris.
Yeah, actually, it's interesting. Every code demonstration today just worked for everyone. That's pretty unusual.
Well, that's because we have great speakers at GeekOut.